Hello everyone. In this lesson, we are going to take a look at acid and base strength and their molecular structures. Please read the OER textbook that's available on Moodle for chapter 14.2. Before we can talk about acid and base strength, we will first review the concept of electrolyte versus non-electrolyte from Chem 122. The non-electrolyte are the substances that do not dissociate when dissolved in water. Thus, there is no ions that can conduct electricity. As you can see from this diagram here, you will see that the molecules stay intact. On the other hand, electrolytes are the substance that can dissolve and dissociate in water and give ions that can conduct electricity. As you can see from these two examples, both strong electrolyte and weak electrolyte do dissociate to give ions, and they both can conduct electricity. However, the difference between strong electrolyte and weak electrolyte is that strong electrolyte, when it dissolves in water, is fully ionized, is ionized 100%. Versus when you look at weak electrolyte, as it's dissolved in water, it's dissociated only partially. Thus, the strong electrolytes would be able to conduct electricity way better than the weak electrolyte. From last term lecture, you got to see the lecture demonstration about the electrolyte versus non-electrolyte, and these are examples of the solution that we test out. We look at deionized water, tap water, solid sugar, sugar solution, vinegar, solid table salt, salt solution, hydrochloric acid, sodium hydroxide solution, copper 2 sulfate solution, and Gatorade solution. And you can see that all of these has a different conductivity. You probably notice that many of them are not able to produce light or turn on the light bulb, and some of them are able to turn on the light bulb, and some of them have a different brightness of light as well. From these observations that we made from last term, we can conclude that the strong electrolytes are those solutions that contain salt, and those what do we mean by salt is ionic compound, and there is one molecular compound here. We will talk about that later. And the weak electrolyte are acetic acid, which is molecular compound as well, and tap water that contain ions, for example, fluoride ions, chloride ions, and non-electrolyte are those solid, and also those are molecular compound. Okay, so that means the conclusion from this observation from last term, we can conclude that substances in solid state are non-electrolyte. They will not produce ions because the ions are fixed together in crystal structure. However, when those ionic compounds dissolve in water, they are going to dissociate, that they will be able to give off ions. So that's why all the salt solutions are strong electrolyte. Now, for molecular molecule, most of molecular molecule are non-electrolyte except acid, and we can classify acid as either strong or weak acid. So today we are going to take a look at the strength of the acid, because some of the acid can behave as either strong electrolyte or weak electrolyte. Based off the electrolyte concept, the strength of acid and base can be described as the extent of dissociation or ionization in water. Strong acids such as hydrochloric acid will fully dissociate into ions. These ions allow for electrical conductivity. Again, since strong acid fully ionized, you can see that there is no molecule of acid left in the solution. There will be just ions present in aqueous solution. On the other hand, weak acid such as acetic acid only partially ionized. As you can see in this beaker right here, most of the molecule of acetic acid still intact, except few molecules that do dissociate to give off proton. Next, we are going to take a look at the list of strong acids and bases that completely ionize when dissolved in water. There are 6 strong acids that you need to memorize. One is hydrochloric acid, followed by hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid. And there are 6 strong bases that you will need to memorize: sodium hydroxide, potassium hydroxide, lithium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. Again, you must know these 6 strong acids and 6 strong bases, because anything that is not on this list, those will consider to be weak. To represent the ionization process of strong acid and bases, we are going to use one head arrow to represent that it's going to ionize 100% or fully ionized. To write a balanced ionization of hydrochloric acid in water, first you will need to write the chemical formula of hydrochloric acid. The word hydro tells us that there is the hydrogen that written in first, followed by chloric, which come from chlorine. And this is an acid that is in aqueous solution, so the phase for this would be AQ. So we are going to react with hydrochloric acid with water. And again, because hydrochloric acid is a strong acid, we are going to use the arrow with one head, and then we are going to transfer the proton. The species that's going to give off proton is an acid, hydrochloric acid. So that means the hydrogen will transfer from hydrochloric acid into water. What happened next would be, because it gives off a proton which has one positive charge, the leftover would be chloride ions with one negative charge. And because water accepts proton from hydrochloric acid, water will become its conjugate acid, hydronium ions. Recall from the previous chapter section, hydrochloric acid is an acid, and the chloride is its conjugate base. And in this case, water behaves as a base, and its conjugate acid would be the hydronium ion. Next, let's take a look at ionization of calcium hydroxide in water. Calcium has a 2 positive charge. Hydroxide is a polyatomic ion with 1 negative charge. So that means every 1 calcium is required 2 hydroxide ions. So in this case, the chemical formula of calcium hydroxide would be Ca parentheses OH subscript 2. And we are going to ionize this compound into water, so you're going to react with water. Calcium hydroxide is a strong base, so that means the base in this case would accept proton from water that will behave as an acid. Again, proton would transfer from acid to base. And you probably noticed that calcium already has 2 positive charge. So calcium is not going to be the species that accept proton. The species that are going to accept positive proton would be hydroxide ions. Because we have 2 hydroxide ions in the molecule, so that means it's going to accept proton transfer twice. So we will need 2 water molecules in order for the 2 hydroxide ions in calcium hydroxide to accept 2 proton. The result of this reaction would be calcium 2 plus 2 hydroxide ions that accept proton. This species is the same as water. So I'm just going to write 2 water. And as 2 water molecules lose 2 proton, so those 2 water molecules will become 2 hydroxide ions. From this equation, you can see that water appears on both sides of equation. So that means I can cancel water on both sides of equation. Therefore, the simplified balanced ionization of base would include only calcium hydroxide undergo ionization to produce calcium ions and hydroxide ions. As you see in the final equation here, I don't need to include water molecule when I write base ionization. Now let's consider strong polyprotic acid, such as sulfuric acid. As I mentioned earlier, the first ionization is going to be fully dissociated. So that's why we are going to use one head arrow. However, for the second dissociation is only partially ionized. So that's why we are going to use the reversible arrow with two heads that go forward and reverse, indicating that hydrogen sulfate will dissociate to proton and sulfate ions, and at the same time these two can also recombine to make these hydrogen sulfate ions as well. Next, we are going to take a look at weak acids and weak base. Anything that are not on the 6 strong acids and 6 strong base list, we will consider them to be weak. And again, weak acid and weak base are the one that partially ionize into proton or hydroxide ions. Let us take a look at weak acid first. What happens when weak acid react with water? When weak acid react with water, it will produce only a small amount of proton. So the acid that I'm going to use as an example today is acetic acid. Acetic acid is not one of the 6 strong acids, so that's why acetic acid would consider to be weak acid. When weak acid react with water, it's going to transfer proton into water. So proton would transfer. And then the weak acid then will become its conjugate base, acetate ions. And as water accept proton, then water will become hydronium ions. Here are the list of some common weak acids. You do not need to memorize this list because as long as you know what are the 6 strong acids, you would know that anything that is not on that list would be weak acids. Now let's take a look at weak base. And similar to weak acid, weak base will react with water and will produce only small amount of hydroxide ions. And again, in this case, ammonia will behave as a base. Ammonia will accept proton from water, so that means in this case, water will be the one that transfer proton to ammonia. Then ammonia will become ammonium ions, and as water lose a proton, it will become hydroxide ions. Notice the reversible arrow in this case for weak base. Here are some common weak base. You do not need to memorize this list because as long as you know what are the 6 strong base, anything outside that list would consider to be weak base. Note that other base would contain a negative ion because this negative will attract to the proton, right? Because base accept proton. Or those the one that have a lone pair. So of these compound that contain nitrogen, those nitrogen contain lone pairs of electron that can accept proton as well or attract to proton. So that's why they would behave as base. Next, we are going to take a look at what make acid and base strong or weak. First, we're going to take a look at binary acid. Binary means two. This acid contain 2 elements. One is the hydrogen and the other one can be any species or any non-metals. Again, when the acid dissolves in water, it's going to dissociate into proton and its conjugate base. These protons can react with water and become hydronium ions, but just to simplify this, I'm just going to leave it as a proton. The strength of the acid comes from the attraction between proton and its conjugate base. Strong acid can fully ionize. That means the bond between conjugate base and proton would be weak. The weaker the attraction, the acid would be stronger acid. Acids are molecular compound, which means the bond between hydrogen and its conjugate base is a covalent bond. Covalent bond means that the electron will be shared between hydrogen and its conjugate base. If atom A has high electronegativity value, it's going to withdraw electron toward itself away from hydrogen. So that means the electron density would go toward more of the A than hydrogen. The more polar the covalent bond is, it's going to be easy to break this bond between hydrogen and A. So the molecule will give off proton easily. Thus, this acid would be a stronger acid. In conclusion, we can say that by increasing electronegativity of A, the HA bond will become more polar and it's easier to give off proton. So that means the acid would be a stronger acid. Now let's consider the periodic trends. As you see, going from left to right, you are increasing electronegativity values. As the electronegativity values increase, bond polarity will also increase as well. That means the molecule will give off proton easily and the acid strength will increase. Note that the acid strength trend would be the opposite from the base strength trend. Now let's consider going from top to bottom of the periodic table. Moving from top to bottom of the periodic table, the size of the molecule will get bigger because as the number of shells increase, the size of each of those atoms will increase as well. So that means it's going to make the overall molecule to get bigger. As the bond length increase, the attraction force between the two atoms will be a little bit weaker. So that means it's going to end up with a weaker attraction. So that means the molecule will give off proton easier. That means the acid strength will also increase as well. This is the main reason why HF is not part of the 6-strong acid, because the strength between hydrogen and fluoride is very strong. That fluorine doesn't give off hydrogen easily. It wants to hold on to it. So that's why hydrofluoric acid is not one of the strong acids. Next, let's take a look at molecules that contain more than 2 elements. Ternary molecules are the molecules that contain this generic structure. And this type of compound can be acidic, basic, or amphoteric depending on the property of the central atom E. If atom E has high electronegativity value, the bond between hydrogen and oxygen would be more polar because the electron density would be withdrawn toward oxygen and E, making this bond right here to be very polar, so it's easy to be broken. So that means hydrogen would be give off easily, so that would make molecule to be an acid. On the other hand, if E has relatively low electronegativity value, the bond between E and oxygen, which is bond A, would be very, very polar. So that means this bond would be able to break off easily. So this type of bond would become an ionic bond. And we can classify this as a base because if this bond is break easily, it's going to break right here and it's going to give off hydroxide ion instead. Ternary molecules that are acid, we call this type of acid oxyacid. The type of atoms that have relatively high electronegativity are those of nonmetals. So that means if you see the ternary molecule that contain nonmetal that connected to oxygen, we can classify those type of acid to be as oxyacids. Sulfuric acid is an example of oxyacid. Again, as you see, sulfur is a nonmetal, and as nonmetal sulfur connected to oxygen, sulfur has relatively high electronegativity, so that means it's going to withdraw electron. It's going to help oxygen to withdraw electron away from hydrogen, making the bond between hydrogen and oxygen weak. So that means it's going to be easy to give off that hydrogen. So that means this molecule would classify as an acid. Another example is perbromic acid. Again, bromine is a nonmetal. It has relatively high electronegativity value that can help oxygen to withdraw electron away from hydrogen, making the bond between oxygen and hydrogen weak. It's easily to give off protons, so that's why this molecule would be an acid. Last example is acetic acid. There are several ways to write acetic acid chemical formula. One of the ways that you see earlier is write hydrogen first, followed by the acetate. Or it can be written as hydrogen and write out the acetate molecule as this. The common way that organic chemists use the most is this way of writing acetic acid. The reason why this one is the most common way is because it actually shows the actual structure of acetic acid. In last chapter of this term, you will learn about organic functional group. The COOH is the functional group that is called carboxylic acid. The name implies that this functional group will behave as an acid. Same analysis that we did earlier. Carbon, which is non-metal, connected to oxygen, and this oxygen connected to hydrogen. This is an example of oxyacid. As you can see that carbon, which is non-metal, would have relatively high electronegativity value that can help oxygen to withdraw electron away from hydrogen. So it's causing this bond to break easily. So that's why this proton right here, or this hydrogen, would be classified as acidic proton. However, these three hydrogens connected to carbon are not an acidic proton. The bond between hydrogen and carbon are nonpolar bond, which means they share electron equally. Carbon doesn't want to give off hydrogen, so that means this part of the molecule is not acidic part. Therefore, as you see, acetic acid is an example of monoprotic acid because it can give off only one proton. Now let's take a look at example of ternary molecules that behave as base. The type of element that have relatively low electronegativity value are those of metals. Again, when you have atom E as metals atom, it's going to make the bond between E and O to be very polar. That means the bond between these two will be broken easily. So these would classify as a base because it's going to give off hydroxide ions. Let's take a look at an example of a base molecule, which is potassium hydroxide. When you write out bond between potassium, oxygen, and hydrogen, you can see that in this case, oxygen is connected to the low electronegativity potassium. Because potassium has a very low electronegativity value, oxygen is going to withdraw electron toward itself away from potassium, making this bond very polar. That means this bond would classify as an ionic bond. Similar to calcium hydroxide as well, when you put this together as the Lewis structure, you can see that calcium, which is not metal, connected to the oxygen, is making this bond right here to be a very polar bond or ionic bond. So that means it's going to break off easily. So you are going to end up with the two hydroxide ions in this case. That's why this molecule would classify as base. Because these two molecules are not molecular molecules, that means it's not a good representation to write out the electron share between metal and non-metal. The better representation of ionic compound would be, as you learned in 121, potassium atom will give off an electron to hydroxide ions. So that means the better representation of this would be potassium ions and hydroxide ions. For calcium hydroxide, calcium atom would give off 2 electrons to become calcium ions, and each of hydroxide ion would receive those electrons. Again, bond between potassium hydroxide and calcium hydroxide are ionic bond. So that means these two Lewis structure would be the best Lewis structure. Here are the examples that you can practice. Please do this before the hangout session because we are going to go over these answers during the hangout session, and the answer key will be provided on Moodle. Thank you for watching.